If you turn to page 514, we can highlight a couple of things here. A function that repeats itself over its domain is called a periodic function, and the amount of time that it takes for it to repeat is called the period. And they give us the graph of sine. Unfortunately, the textbook's scale makes it hard to graph the way they've graphed it. So what I want you to do is right beside that graph, we're going to learn the easiest way to graph the sine graph, and that is using your axes family. So what you're going to do is along your x-axis, you're going to label every family member of your axes family. 2 pi, pi, pi over 2, 3 pi over 2. And then if you use your axes family and you think sine is my y coordinate, sine of 0 is 0. Y coordinate at pi over 2 is 1. At pi, it's 0. At 3 pi over 2, negative 1. And at 2 pi, it's back to 0. If you have those 5 points from your axes family, you can draw the curve of sine. It's a smooth curve going through all of those, and it repeats itself over and over and over again as you go around the circle. So just like your parent graphs in our transformations unit, you have to know what the sine graph looks like. And then we're going to do all the transformations we did in our first unit with the sine graph, with the cosine graph, and with the tangent graph. So being able to quickly label your axes family and get your original graph is going to help us graph the rest of it. Now some other definitions. Some other things that we can highlight, okay? On a sine and a cos graph, the distance from the center line to a maximum is called the amplitude. The center line is what is right in the middle of your graph. And the period of your sine graph is 2 pi. If you were given a graph and asked to find the period, what you could do is you could, for example, you could start at 0. So at 0 on the sine graph, I'm in the middle going up. When is the next time that I'm in the middle going up? Right here at 2 pi. So I could use that to figure out my period. When does it repeat itself? Well, if I start in the middle going up, I have to go to 2 pi to get to the middle going up again. You could take any points. The textbook said, let's start at a minimum. When do I get back to the minimum? Over here. What's the distance between those two? The only problem with this is you'd have to do some more mental math to figure it out, to count how much that is. And there's a couple of ways you could do that. On this graph, you could count that one of these squares looks like it's pi over 6. So if I count from this black dot to this black dot, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that would be 12 pi over 6s, and 12 over 6 reduces to 2 pi. So I could do that. You could go from maximum to maximum, minimum to minimum, or in this case, center line going up to center line going up. Sometimes students go maximum to minimum and then double it. Does that make sense that you could do that? If you wanted to find out how long it takes to repeat itself, if you go from a minimum to a maximum, that's going to be half of the period. you could double it to find the whole period. Some characteristics of our graph. What's the domain of a sine graph? Well, it just keeps on going forever, so we would say the domain is everything. What are the x-intercepts? And this one's a little bit tricky, so we're going to do some work with this. Your textbook says that it's k pi. How do we figure that out? Well, if I started to list them, so you might want to write this down on the side. We list them. There's one at 0, there's one at pi, 2 pi, 3 pi, 4 pi, dot, dot, dot. Same thing in the negative direction. If we started listing them and then looking for a pattern, do you notice that we have positive and negative whole numbers multiplied by pi? 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, and same thing in the negative direction. So if we wanted to write all of them in the same idea that we did with coterminal angles earlier, we can write this as k times pi and define k to be an integer, positive or negative whole number. If we want to figure out the range, we need to know its maximum and minimum. Maximum of 1, minimum of negative 1, so the range goes between negative 1 and 1. Next, on page 515, we have the cosine graph. And just like we did with the sine graph, I would like right beside the cosine graph, I would like you to graph the axis family for your cosine graph. So with your axis family, remember, big idea, cos is your x-coordinate. I've got all of my axis family here. Cos of 0 is 1. Cos of pi over 2, the x-coordinate is 0. X-coordinate at pi is negative 1. At 3 pi over 2, it's 0. And at 2 pi, it's back to 1. So we can use our axis family to graph cos. And similarly, we can highlight some stuff. We've got the same period, same amplitude. The domain will still be everything. But the zeros are tricky here as well. So let's do some work off to the side. Let's start listing them. We have pi over 2 and 3 pi over 2, right? Top and bottom of our unit circle. If we kept going around the unit circle, our next one, coterminal with pi over 2 would be 5 pi over 2, then 7 pi over 2, dot, 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 and same thing in the negative direction. And you might notice a pattern that we always have pi over 2, and here in front it's always an odd number. Now, unfortunately, what I wrote there isn't a mathematical expression. You can't use words and pi over 2. Makes sense, though, always to have an odd number times pi over 2, because we go from pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2, and so on. Now, mathematically, how do we write every single odd number? And we do it the following way, okay? If you take any integer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whichever one you want, and you times it by 2, you will always get an even number. Try. Take 3, times it by 2, you get 6, even number. Take 7, times it by 2, get 14, even number. Take 10, times it by 2, get 20, even number. So does it make sense? Whenever you double any number, it will always be even. So if doubling any number makes it even, if you just add 1 to it, that will make it odd. So this part here, this 2k plus 1, is the mathematical way, as long as we say that k belongs to the integers. That's the mathematical way to write any odd number. This is method 1 for writing the zeros of cosine. We are also going to learn a second method for writing the zeros of cosine. And it's going to build on the idea of what we did with coterminal angles. Do you remember, if I said, what are all the coterminal angles? Let's do it both in degrees and radians just to review. If I said, what are all the coterminal angles with 30 degrees? Do you remember that we did 30 degrees plus 360 degrees times k and said k could be any integer? Do you remember doing that for coterminal angles? So by doing 30 degrees plus 360k, we could say I could add 360 once, I could add it twice, I could add it 3 times. I could add it any amount of times, but no matter what I do, I will always end back at the same spot at 30 degrees. If I did a coterminal angle in radians, so if I did pi over 6 and I said, what are all the coterminal angles with pi over 6 in radians? I do pi over 6 and add 2 pi times k as many times as I wanted. Add it once, add it twice, add it 3 times. So this is the second method for figuring out all of the zeros of cosine. It is noticing that there is 1 here, and if you hopped to the next one, it's always the same jump. What distance is it from the first one to the second one? Pi. Right? And if I jump pi, I would get down here, jump another pi, get back to the top, pi to the bottom, pi to the top. So what we could do as another way is we could start with one of them. I could start with pi over 2, and then I could say I could add or subtract pi as many times as I wanted, and I would get to another one. So this would be another way to list all the zeros of cosine. If you were asked to write all the zeros of cosine, you could choose either method. What makes more sense to you? Noticing the pattern of all odd numbers of pi over 2, or finding one and noticing the pattern of how much you have to jump to get to the next one. And every time you jump pi, you'll get to the next one. Algebraically, if you want to distribute this and simplify, you'll find out that they're both identical. They're both the same equation. And just like sine, the maximum is 1, the minimum is -1, and your range goes from -1 to 1. Just to officially highlight the definition of the amplitude on page 515, the amplitude of a sinusoidal function is the distance from the center line to either the maximum or the minimum. And your amplitude will always be positive. Here's the fun word for the day. Sine and cosine graphs are called sinusoidals. Sounds like some sort of nasal infection that you would get from COVID, but no. The new word of the day, sinusoidals. Kind of has a nice ring. Okay? Right? I know they probably stopped, but if your parents still say, "What did you learn in school today?" When do they stop doing that? Middle school? Maybe they still do it. Right? You could just, we learned about sinusoids. And they'll be like, oh, and probably not ask any more questions. Okay, so turn to page, before we do example 1, at the top of page 516, we will do the tan graph at the bottom of page 516. And once again, the textbook has a tan graph. I would like you to use your axes family and draw it as well. Now for the tan graph, on your axes family you have a couple places that are undefined and a couple places that are 0. Where it's undefined, they show up on the graph as non-permissible values, so we'll have asymptotes on our tan graph. Right? Just like we had asymptotes on our rational graph where you had non-permissible values, we have asymptotes on our tan graph at pi over 2 and 3 pi over 2. And at 0, pi, and 2 pi, negative pi. That's where your tan graph is equal to 0. Tan graph ends up similar shape to an x cubed, doesn't it look like? Except an x cubed doesn't have asymptotes. So it's similar but a little bit different, and the tan graph keeps repeating itself over and over and over again. Yes?
Are we going to be doing any tan graphs on our unit test or the exam?
Possible, yes, it is possible. So we'll practice graphing. There are a lot more sine and cosine graphs than tan graphs, but possibility of having a tan graph could be on there as well. So we're going to have to figure out the same thing here. Period of a tan graph, does it repeat itself? Yes. So if you wanted to figure out the period, you could either take a point, like at 0, it's in the middle going up. When is it in the middle going up again? At pi. So that's really easy to figure out that the period is pi. Or you could take asymptote to asymptote. What is the distance between pi over 2 and 3 pi over 2? That's also pi. So that would be another way to figure out that the period of tan is pi. All right, everybody have it graphed? So we can go back to our highlighter here and highlight period is pi on our graph. There is no amplitude because it goes up and down forever. Some things to write off to the side. The asymptotes, they happen at pi over 2, 3 pi over 2, 5 pi over 2. They happen at the same places as cos is equal to 0. So if we were writing the equations of the asymptotes, we could take the odd numbers times pi over 2, where k is an integer. And you could write it in this form, or if you like the pi over 2 plus k pi, you could do that form as well. Those are all the equations of the asymptotes. If you think about the big idea of tan, remember that one of our big ideas in this unit is that tan is sine over cos. It may make sense that it's the same as the x-intercepts of cos theta. Because wherever the x-intercepts are of cos theta, then you would be dividing by 0 in tan, and we're not ever allowed to divide by 0. When we write equations, and maybe I should write this, equations, the equations of the asymptotes, it's always an equal sign for an equation. That's the definition of all the dotted lines. They're going to be x equals. Now, when we get to the domain, okay, this format actually isn't correct. When you write the domain, this is where you would say there are certain values x can't equal, and you would take those same x-intercepts of cosine. Those are the non-permissible values for tangent. And so for our domain, we say x can't equal those. The x-intercepts of tangent are the same as the x-intercepts of sine. So we've got the same form for the x-intercepts of tangent. And since there is no maximum and no minimum, your range of tangent is everything. Yes? You may. All right, so let's go to example 1. And what we're going to develop is ways of doing our first unit transformations with our new unit and these 3 graphs. And we're also, so each of these asks a specific question. We are also going to graph these to practice our graphing and to hopefully develop a shortcut for doing each of these. Okay? So, from the first chapter that we did, chapter 3 in our textbook, our transformations unit. If you had a 2/3, where it is in this equation, you have to decide, is this vertical or is that horizontal? Is it outside the function or is it inside the function? So our function is sine x. The 2/3 would be outside. It's going to be vertical. This would be a vertical compression because you're multiplying by something less than 1. So we would say that we have a vertical compression and we would have to multiply y by 2/3. You have to have your graph of sine memorized, or be able to use your axes family to quickly graph. So every time you're going to graph sine or cosine, you're going to set up your graph, you're going to mark that the period happens to be 2 pi, divided into 4 equal sections, which is just your axes family. Know that the maximum is 1 and minimum is -1 from your unit circle. And your axes family says sine of 0, 0. So sine starts on your center line, going up to a maximum, back to center line, down to minimum, back to your center line. And so I quickly draw a graph of sine x. And I'm going to look at now, what does it look like if I want to graph sine of 2/3 x? I'm going to draw another graph here. First of all, would you agree if you're multiplying your y values by 2/3, your x values are not changing? So I can remark down the same points of 2 pi, pi, pi over 2, 3 pi over 2. I can put my axes family back down. That's going to be the same. And you're going to notice that we are going to develop a bit of a shortcut for sine and cosine. Instead of drawing, you know how we used to take the points on our original graph and draw the arrows? This one gets a little bit annoying if you draw the arrows because your points are going to be like pi over 2 comma 1, pi comma 0. Not nice numbers to do mental math with. So we're going to develop some shortcuts so that our mental math is easier for us. In this case, we are going to notice that, well, wherever I had x-intercepts and my y values are 0, those ones are going to stay the same. Because if I multiply by 2/3, they'll stay the same. If I look at one point, let's say I looked at pi over 2 comma 1, and I multiplied my y value by 2/3, Does it make sense that I would get pi over 2 comma 2/3? And similarly, when you multiply the 1 by negative 1, your minimum value, which was negative 1, is now negative 2/3. And this will be our shortcut for our amplitude. When you have a vertical stretch or compression, you are going to change your amplitude. And so your maximum and minimum is going to change. And all we'll do is we'll make some changes along our y-axis. So instead of going up to 1 and down to negative 1, I'm now going up to 2/3 and down to negative 2/3. And a pattern we're going to notice for a sine graph is going to start in the middle. And as long as you have your axes family or your period divided equally into 4 sections, the sine graph will always go middle, max, middle, min, middle. Over and over again. Part B, we have a cosine graph. We have a negative 4 out in front of our cosine graph. So first, I'm going to graph my cosine graph. I know it as a max of 1, a min of negative 1. I put my axes family on here. One period is 2 pi divided into 4 equal sections. Just labeling my entire axes family. And a cos graph starts at 1, starts at a maximum. Then it will go center line, minimum, center line, maximum. This negative 4 is going to be a vertical reflection and a vertical stretch. We'll multiply our y values by negative 4. What does that do to our graph? Well, it doesn't change my x values, so I still have a period of 2 pi. I can label my axes family. Divide this into 4 equal sections. But now, instead of starting at the point 0, 1, if I multiply my y values by negative 4, does it make sense that I would have 0, negative 4? My minimum now becomes negative 4. When I multiply by 4, my maximum will now become positive 4. And if I'm starting here at the bottom, and this is where the shortcut comes into effect, okay, cos graph will go from the minimum to the center line. Next one, a maximum. Back to a center line, back to a minimum. And I mean, you could take each of these points. For example, here we have pi comma negative 1. If I multiply that y coordinate by negative 4, I'm going to get pi comma 4. Draw a nice smooth curve through all 5 of those points. And we have just graphed y equals negative 4 cos of x. So shortcut, okay? And what did the question originally ask us? In the first one, it asked us, what's the amplitude? Here we're going to say the amplitude is 2/3. For the second one, what's the amplitude from the center line to the maximum? So even though there's a negative 4 out in front, when we're talking about amplitude, it's always a positive number. The negative meant that there was a reflection, but the amplitude is still the distance from the maximum to the center line. That amplitude is 4. So the first shortcut that we're going to notice for our sine and our cosine graphs is that if you have a number out in front, a vertical stretch or compression, that is going to change your maximum and your minimum, and it's going to change your amplitude. A number out in front of 4, amplitude is 4. Number out in front of 2/3, amplitude is 2/3. If you had a 7 out in front, your amplitude would be 7. So that'll be our first shortcut, that our amplitude is going to be figured out by whatever your vertical stretch or compression is. And if we know our amplitude, we can label our maximum and minimum very easily, and this will allow us to graph it quicker than if we had to draw all the 5 points and say, where does this one go, where does this one go, where does this one go? So it will save us some time on mental math. Questions I'd like you to circle: 3A and B, 4, 5, and 9.